Hey everyone, Ricardo here, and in this video I'm going to be showing you how directional comparison blocking, commonly known as DCB schemes, work. Now this is a type of what we call pilot scheme, which means a protection scheme where two ends of a transmission line communicate with each other to declare a high-speed trip for faults inside of the transmission line. Now to do this we implement overreaching elements, that is protection elements that can see faults beyond the end of the transmission line. This way, each end of the transmission line can see faults in the forward direction. Now, because these elements can see faults that are beyond the end of the transmission line, in a DCB scheme, we also implement a reverse-looking element that can send a blocking signal to the remote end if it sees a reverse fault. Now, that's the main difference between a permissive scheme, such as the POTT scheme that I talked about in this video over here, and a blocking scheme, such as the DCB scheme. In other words, in a permissive scheme, such as the POTT scheme, a relay will trip once it gets permission from another relay, while in a blocking scheme, such as the DCB scheme, the relay will go ahead and trip unless it gets blocked by another relay. So that's the key distinction between a permissive scheme and a blocking scheme, again, such as the POTT scheme and a DCB scheme, which are two types of pilot schemes for transmission line protection. Now, before we go deeper into how DCB schemes work, make sure to hit the subscribe button. We always post videos here about power engineering and power system protection and control. All right, so let's look at an example transmission line to see how we can implement a DCB scheme for high-speed protection. All right, so let's say, for example, that we're trying to implement a DCB scheme for this transmission line that I have over here. In this case, we can see the transmission line's positive sequence impedance. If I go over here to the impedance tab, and we can see that the positive sequence impedance is 0.69806 plus J 4.21257. So this, again, is the positive sequence impedance, and of course the negative sequence impedance of the transmission line, as it is typical, is the same as the positive sequence impedance. And we can also see here the zero sequence impedance, which for this example transmission line is 2.04572 plus J 12.8622. So this is, of course, the resistances, and this is the reactance. So what we could do in this case is implement overreaching distance protection zones, what we would typically call a zone 2 for both phase and ground faults at each end of the transmission line. Now these will see faults in the transmission line and at the remote bus. So for example, if we implement an overreaching zone 2 element at this end of the transmission line, so on this relay over here, the 411L, that will see faults in the transmission line, but also at the remote bus, because again, it is an overreaching element. So we'll see faults here, for example, in the transmission line, so over here, but it will also see faults beyond the transmission line, as for example, at the remote bus, which we of course do not want to trip high speed for that, because that would miscoordinate with whatever protection there is at the remote substation. Now to prevent this, we can implement a reverse looking element that will send a blocking signal to the remote end once it picks up. So for example, for this fault over here, which is beyond the end of the transmission line, we can implement a reverse looking element on this relay over here, typically what we would call a zone 3 element. And that reverse element will also see this fault, and it will see that it's in the reverse direction, and will send a blocking signal to the remote end. So even though this end, the left side in this case, which I'm going to call the local end, even though that end sees the fault in the forward direction and it's trying to trip, it's going to get a blocking signal from the remote end from this relay over here, because this relay is seeing it in the reverse direction. In other words, we need to implement both a forward zone 2 and a reverse zone 3 at each end of the transmission line. The zone 2 is going to look in the forward direction, and the zone 3 is going to look in the reverse direction. And the zone 2 is going to try to trip unless it gets blocked by the zone 3 at the remote end. So for example, if we have a fault at the remote bus, the zone 2 at the local end is going to pick up for that fault, but the zone 3 is also going to pick up, which is looking for reverse faults, and it's going to send a blocking signal to the zone 2 at the other end. So let's take a look at the impedance plot for this example. All right, so here let's use the positive sequence impedances only. I'm going to be focusing here on the phase elements, although a similar process would apply, of course, for the zero sequence impedances for ground faults. And here I'm also going to be using the primary impedances. Just know that, of course, if you were to enter these numbers into a settings file, you would need to convert all the impedances to secondary impedances, as opposed to primary impedances. But just to keep things simple, I'm going to use primary impedances. All right, so again, from our model, we saw that the transmission line impedance, and I'm converting here to polar form, was 4.27 at an angle of 80.59 degrees. So this plot over here, again, is the transmission line impedance. Now we then know that we want to implement an overreaching zone 2 at each end of the transmission line, And we can use a typical setting of 120% of the transmission line's impedance. So for our zone 2 reach, then we can enter 1.2 times this number, which is roughly 5.12. And you can see that our zone 2 here is essentially an overreaching element that reaches beyond the end of the transmission line. And again, and this is important, both ends will see faults beyond the transmission line. So we would also have a zone 2 at the remote end with the same number, so 5.12. And you can see over here that the local zone 2 is this one over here. It reaches beyond the end of the transmission line. And the remote end zone 2 is this over here, which also reaches beyond the end of the transmission line from its perspective. Now here, the overreach, that is the amount by which the zone 2s see beyond the end of the transmission line, is 20% of the transmission line because we've set the reach at 120%. So each zone 2 is reaching 20% beyond the end of the transmission line. And in this case, that's roughly 0.85 ohms primary. Essentially the difference between this number and this number over here. And again, we can see that over here. So for example, in this case, the remote bus is over here. And you can see that the overreach of the zone 2 is essentially this amount over here. So it's roughly 20% of the transmission line impedance. So let me get rid of this. Now what we need to do here is again implement our zone 3, which is going to be reverse looking, which will send a blocking signal to the remote end, preventing it from tripping when it picks up. Now the reach of the zone 3 is somewhat arbitrary, with the constraint of course that it must reach beyond the overreach of the zone 2. So let me actually get rid of the remote zone 2 so that I can show you that. So I'm getting rid of this, and here again, this is the local zone 2, which is overreaching the transmission line by 20%. Now for example here, if we implement a setting of 1 ohm for the remote zone 3, so this one over here, we can see that it sees past the overreach of the local zone 2. In other words, the zone 2 at the local end is reaching up to this point, but the zone 3, which is looking in the reverse direction from the remote end's point of view, is reaching up to this point. So the key point here is that the zone 3 must reach beyond the overreach of the local zone 2, such that for any external faults outside of the transmission line, it gets blocked by the zone 3 at the remote end. Now this margin is somewhat small. Typically we would want this coverage to be rather large, at least 3 to 5 times the overreach of the zone 2. So in this case, for example, a better setting would be something like 3 ohms for the zone 3. And this, as you can see, provides plenty of coverage for making sure that we block for external faults. You always want something like this. The zone 3 should be rather large in comparison to the overreach of the zone 2. Now notice what I'm saying here. It's rather large in comparison with the overreach of the local zone 2, not in comparison to the zone 2 setting. In other words, this number over here for the remote zone 3 needs to be typically 3 to 5 times larger than this over here, the overreach of the zone 2. In other words, how much it reaches beyond the end of the transmission line. Not in comparison to the setting of the zone 2 itself, just in comparison with the overreach beyond the end of the transmission line. So these are somewhat appropriate settings for our zone 2 and our zone 3 based on the transmission line impedance over here. So now what I'm going to do is I'm going to add the local zone 3, and I'm going to set that the same 3. And you can see that essentially that's a reverse looking zone with 3 ohms reach. And the remote zone 2 is also 5.12. And again, the way this scheme works is by tripping high speed on the zone 2 elements at each end unless they receive a blocking signal from the remote end, which comes from its zone 3. So for example, for a fault in the middle of the transmission line, so let's say that we have a fault over here, both zone 2s will pick up because both will see it in the forward direction. And in this case, none of the zone 3s will pick up because the fault is, again, in the forward direction, and those are looking in the reverse direction. So in this case, both ends are going to trip high speed because they're not going to get blocked by the remote end zone 3. Now note here that we, of course, need to allow some times for the blocking signal to come in from the remote end. So the zone 2s usually have a delay, but a very short one, typically in the range of 1 to 3 cycles, depending on the communications channel. Now this is essentially just a short time to see if the blocking signal comes in from the remote end. We of course need to allow some time for the blocking signal to come in if it's going to come in. Now, because we know that that signal shouldn't take too long to come in, we can just say, well, go ahead and trip within 3 cycles, for example, if you don't see the blocking signal coming in from the remote end. Now, this is of course much faster than the typical zone 2 delay, which is around 30 cycles for a non-communications assisted tripping scheme. So we were not implementing a DCB or a PTT scheme, essentially any type of pilot scheme. The zone 2 would have a delay usually around 30 cycles. Now, just as another example, let's say that we have a fault that is beyond the transmission line at the remote substation. Let's say that we have a fault somewhere around here, and this could be a fault in one of the transmission lines that go out of the remote substation to some other substation. Now, the local zone 2, this one over here, is going to pick up because that fault falls within its zone 2. Now, the remote zone 3, this one over here, is also going to pick up because it's seeing it in the reverse direction. And in this case, the local zone 2 would try to trip, but it's going to get a blocking signal from the remote zone 3 because it saw it in the reverse direction. And this will prevent the local zone 2 from tripping high speed, which is again what we want, of course, because we don't want to trip high speed for an external fault. All right, so that's how DCB schemes work. And I'm going to be making this spreadsheet available for download. Check out the link in the description below. And of course, if you like this video, make sure to hit the like button and subscribe to the channel for more videos about power engineering and power system protection and control. And we'll see you in the next one.